Great presentation, and we should immediately with questions, please. Lively, spicy discussion, please. Please.
Alkaline versus solid is important, but how about oxygen fugacity? For both talks, I think oxygen fugacity can affect the stabilization, early stabilization or later stabilization of different mineral phases. I'm not an isotope geochemist either, anyways, but
yeah,
I think
question.
oxygen fugacity could affect that as well.
Are the isotopic fractionation factors influenced by FO2? And I think we can answer that right now we don't know. It would certainly be something worth investigating. One of the things I was very surprised about regarding, well, I've been surprised by a lot, actually, regarding vanadium isotopes, but one of my expectations and one of the reasons for doing the diamictites in the first place is that what I didn't talk about is that these diamictites all have a weathering signature, and because the glaciers were scraping off regolith, or weathered rock, and I would have expected vanadium isotopes to fractionate during weathering, oxidative weathering at least, when you can have multiple valence states of the element. But all of the studies that have been done so far on weathering profiles, some of them yet to be published, show no variation through these weathering profiles due to oxidative weathering. So that was a surprise to me. I think, but certainly some experimental studies, I mean, all of these stable isotope systems, I think we need some good experimental work to try to constrain what are the fractionation factors in igneous systems and the most important phases, but presumably it's the iron titanium oxides that are generating this.
I might just add, I didn't talk about it on purpose. And the reason for this is, if you do water undersaturated experiments, it's very hard to buffer the oxygen fugacity. And when you leave the fractionated assemblages evolve, you see that the iron 2, iron 3 ratio changes because the different minerals that fractionate, they don't take the same amount of iron 3 to iron 2. And maybe by purpose, we did the right thing because we didn't buffer. Maybe this is how magmas evolve in chambers. And there is papers out that postulate these, that during fractionation, the oxygen fugacity is increasing. Okay, but in the experiments, we didn't buffer them because we started with undersaturated experiments.
Thank you very much.
Questions? So, I have a very quick question for both of you. Please do not fight. So, the studying Earth's crust has also very important societal implications, like, for instance, mineral or resources. So what do you think about understanding composition and probably forecasting where we can find resources, especially where we don't have direct access to the Earth's crust? What do you think? What should be done, to interact more with the geophysicists, for instance, so like petrologists are not only working between in their own club, but they start to interact with other scientists.
Well, so I'm not sure I understand your question exactly. You're asking about natural resources?
Yeah, natural resources, for instance, or in general to understand the Earth's crust, how to deciphering Earth's crust, also using other complementary tools like geophysics.
Well, okay, so to get at the lower crust, since we don't have many samples of it, we've got a few cross sections, we've got some xenoliths from here and there. Xenoliths, you never know how representative they are, which is always a problem. So that's where we have tried to bring in geophysical data to try to place some constraints on what might be in the lower crust. And there is a pretty good correlation, in fact, between seismic velocity and average silica content. For example, we can look at laboratory measurements of different rocks, granulites or amphibolites, and see these correlations. And that was the whole rationale back, I don't remember how many years ago now, a long time ago, when we started trying to estimate the deep crust using average geophysical properties like average P-wave velocity. There's a whole lot more data out there now for P-wave velocities over the globe. especially in the US, due to programs like EarthScope, for example, lithoprobe in Canada. We also can use heat production, and we tried doing that too, because we know what's coming out the surface in terms of heat flow, and if we go to areas of conductive heat flow, then we know that there should be a mantle component and a crustal component, and if we can put some constraints on the mantle component, which is not always easy, but it's something we're working on, then we can use the surface heat flow to estimate the crustal heat production, and that will tell us something about the composition. There is a correlation between heat production and, mafic versus felsic igneous rocks. The problem comes in both from the geophysical, from the seismic perspective, and also from the heat flow perspective, that metasediments, which you have in the urea, and actually I have a question for you, but after this, metasediments can have just about any P wave velocity you want, because if they're melted and you remove the quartz component, you're left with very high density phases like garnet and silmonite, and you can get P wave velocities approaching 8 kilometers per second, which is ridiculously high for the crust. On the other hand, if they have a lot of quartz component, then they're going to have low P wave velocity, so they can be all over the shop. But their heat production actually is going to be high, because there are phases that hold back, refractory phases like monazite, that hold back heat-producing elements. So even if you melt it, you still have relatively high heat production. So that could be a way of trying to decipher. But a question I've been pondering, and Othmar, maybe you can tell us about this, is we see Ivrea zone, there's plenty of metasediment in the lower crust. We see some xenolith localities like Kilburn Hole, where there's these beautiful high-grade metapelites. How did they get down there? And how do you get sediment into the lower crust and keep it there in a normal thickness crust? This is something that's always been rather mysterious to me. So, do you have any thoughts?
Some speculations, not more. The fact that they're associated with mantle rocks, with carbonates, they look very much like passive margin sequences where oil companies drill to find the last pieces of oil. And for some reason, you get cinder crust, exhumed mantle, and you put sediments on top. And these are the first areas, if you get convergence, that might get attached to somewhere in the deeper crust. Exactly where is difficult to predict, but the mere fact that they are so variable and incorporate peridotites indicates to me that this is probably a passive margin sequence that was reactivated, and this is the first one before the oceanic crust gets abducted, that this can stuck to the continent and doesn't get eroded by subduction erosion in some places. Okay, but that's pure speculation.
So your Ivrea estimate, though, was much less refractory than, say, the Hacker estimate. In terms of the uranium and thorium, you have huge negative anomalies in uranium and thorium for the Hacker estimate. And probably because of these metasediments, you have nothing like that. And I'm just wondering how representative that can be further back in time when you go to Archean crust and you see that it's clearly had time evolution low uranium thorium because they look very unradiated layers.
Well, that's again, is a very difficult question given the area of the Ivrea which is accessible. It's not hundreds of kilometers. And what I didn't tell you is the representativity of the bulk rocks that you saw. Okay? And I did this on purpose because I would feel ashamed to show you the data this way. People mainly analyzed almost 20% of the peridotites, and from the sediments, we get 50 analyses. So there is a very big bias. So before I would say it's very typical for that age, I would like to have a gridded analysis and to get more, to be sure that we get representative data, especially these trace elements could be, for some reason, enriched. Okay? So I would take it with a grain of salt, and maybe with drilling a complete section of metasediments and analyzing it is more representative than just somebody taking 20 samples. We will see that in the future. So I can't really answer, sorry.
was interested to see that your wet experiments appeared to suppress plagioclase fractionation, and yet from my third-year igneous petrology, I remember that one of the hallmarks of wet crystallization in andesites is the ability to generate these really high anorthite content plagioclases, because you flatten the plagioclase liquidus solidus loop. Well, so the question is, A, is that still valid? And B, could we use that as an indicator of subduction, initiation of subduction zones, the presence of high anorthite plagioclase?
So it's totally valid. The funny thing is just if you do hydrous experiments at 1 GPa with a normal basalt without anything special, you crystallize a lot of ultramafic minerals first before you saturate in plagioclase. And we were also afraid of that this is composition dependent, but it isn't. So until you get to plagioclase saturation, you need to fractionate 30, 40, maybe 50% of mafic, ultramafic minerals. Okay? And then you're at the andesite, and from there on, you get anorthite 85, anorthite 90. Okay? And to make the link to the ore deposit question, I think the beauty of these experimental studies is to show that the amphibole stability is everywhere, and amphibole and porphyry copper deposits are increasingly recognized that there's a tight link where we get hydrous fractionation. So I think these rather tedious experiments, they have a great value in terms of estimating how much water or fluids could be liberated. Obviously, we didn't analyze any resource metals in these experiments. It was mainly major elements. But the hydrous fractionation, I think, is very relevant for a part of our deposits.
I can probably do it without a microphone. I wanted to ask you a question, Roberta, about the changing composition that you see, let's say, from 3.3 to 2.4 of that interval, which you related in part to changing composition and mass of the crust. There are two pieces of information that I think are quite interesting. In the summary volume for the superior province of the lithoprobe program, John Percival summarized pressure across the entire superior province on a map that included estimates of crustal thickness. And the interesting thing about that was that the pressure varied very little across the whole of the superior province, and neither did the crustal thickness. Looking at the Google image of the Pilbara, although we don't have the same information, my guess would be from the fact that we have granite domes all the way across, that that's probably a uniform, approximately uniform level of exposure as well. And that, I think, would be different than we might see on a plate margin process at the present day, and probably different than a plate margin process in the Proterozoic. The other point is that prior to 3 or 3.2 or whatever, we had almost nothing above sea level. There was, in that sense, no continents. And so we have the material that's now above sea level, that was coming above sea level through the late Mesoarchean and Neo-Archean. And so there's an issue of it's apparently coming up without being tilted or without producing variations in what appears to be exposure level pressures. So it's some process other than plate margin processes, perhaps. And I wonder whether that can somehow create, by having more stuff above sea level and more erosion, we might actually change the composition of what's being seen in the sediments as a consequence of that, rather than necessarily a change in dynamics before the Proterozoic.
Well, so we do have shales that go back to about 3.5 billion, and right, and it just seems that all of the shales. So we obviously have to have crust above sea level in order to generate a terrigenous sediment. So whatever was exposed to erosion and weathering at that time was considerably, had much higher transition metals, et cetera, right? Yeah, so.
Are there further comments, questions, or you really die for a coffee? Coffee is not Italian espresso, by the way. If you need coffee, Once again, thanks to the speakers.